This is Algebra 2, Section 1.4a. We're just going to get started with 1.4 today, but the learning target for Section 1.4 is that students will be able to solve linear systems of equations by graphing. For the warm-up, we're going to try something new. I'm going to see if we can kind of lead ourselves to the answer about how we solve a system of equations like this. So I'd like everybody to pause the video and graph y equals 2x plus 1 and y equals negative x plus 4 on this same graph here. Now what you can do, you have a couple of different options. You can either use the fact that it is in slope-intercept form, so that tells me my y-intercept and my slope for both of these, or you can use the table method where maybe you fill out some points for, say, let me change this to black. We've got negative 2, negative 1, 0, 1, 2. You can just plug in those points into our equation here. For both our first equation, we have 2x plus 1, and then y equals negative x plus 4. Once you've filled out this table or graphed the two lines just from the slope-intercept form, see what you can find that is common about those two lines. So go ahead and pause the video, try it on your own. I'm going to go ahead and finish it up. So if I plug in negative 2, I get 2 times negative 2, which gives me negative 4, plus 1, I get out a negative 3. So I'm going to follow that same process for each one of these x values that I'm putting in. Now I'm going to plot those points over here. Negative 2, negative 3, negative 1. And if you did just use the, plot the y-intercept, and then use the slope to find other points, we should get out the exact same line. Do my best to draw that straight there. Might want a ruler for this section, I'll tell you that. Now for our next one, I'm going to do the same thing. If I plug in a negative 2, and then I make it negative, or the opposite, it becomes positive. So I get 2 plus 4, that gives me a 6. I'll do the same thing for these other points. I then go ahead and plot these as well. So negative 2, 6, I believe that's off my chart there, so I'll start with negative 1, 5. There we go. I now have two lines, and what I'm trying to see here is, what do we notice about the lines graphed above? What do we recognize from the table? Well, hopefully you can see that they share a point. They intersect, and they intersect at the point 1, 3. So let's fill that out. They share a common point, which means they intersect. That was at the point 1, 3. So let's go ahead and realize that, we're working on a new learning target, which is how to solve a system of equations by graphing. So let's define, what is a system of equations? Where it is a set or collection of equations that solve all at once. What we are trying to do is we are trying to solve for that intersection point. Trying to solve for intersection point. When you solve a system of equations, your solution will hopefully be the coordinate point. So for instance, for the example that we did in the warm-up, if I was asked, what is the solution to the system of equations, I would say the coordinate point 1, 3. That represents my solution. Let's look at a couple of examples below. How do we know when we have a solution? When we have an ordered pair, when we have a coordinate point, however you kind of think about the vocabulary there. when we have an ordered pair that works in both equations. Notice I've capitalized both. It has to work in both equations. So let's ask ourselves this question. Is 2, -3 a solution to this system of equations? Well, in order to find out, I need to plug in x equals 2 and y equals -3 into both of my equations, and I need to get true statements for both. So let's go ahead and plug in those values to our first equation. I have -3 times my x, which is 2, minus 2 times my y, which is -3, equals 0. I get -6 plus 6 equals 0. Make sure I can have enough room here. Is that a true statement? Yes, it is. That is true. It works in my first equation. Does it work in my second? We have to check both. So I get 5 times 2 plus my -3 equals 6. Does 10 minus 3 equal 6? No, it does not. So therefore, is 2, -3 a solution to this system of equations? The answer is no. I encourage you to pause the video and try the next group of equations on your own. Is -1, 2 a solution? Well, I'm going to plug in x equals -1 and y equals 2 into both of these equations to check. Works in the first equation. Oh, we're running out of space. Works in the second equation. Hopefully we can all see that says equals -6 there. So since it works in both equations, I get true statements in both of those. The answer to this question is yes. We will go on and continue this in our next video, but for now, you should have enough information to complete the 1.4a worksheet. Thank you.